Look up at the night sky on a clear evening, and you see a familiar tapestry of twinkling lights. It feels permanent, serene, a celestial map that has guided humanity for millennia. But out there, hidden in the vast darkness between the stars, are monsters. They are regions of space where gravity has become so impossibly strong that not even light can escape their grasp. They are black holes, and they represent one of the most profound and terrifying mysteries in the entire cosmos. What you think you know about the universe, the rules of space, the flow of time, the very nature of reality itself begins to unravel when you approach the edge of one of these cosmic anomalies. They are not just empty holes, they are engines of extreme physics, gateways to the unknown, and the ultimate expression of nature's power. Today, we are going on a journey to the edge of understanding. We will explore 30 incredible facts about black holes, each one designed to challenge everything you thought you knew. We will see how a black hole can stretch an object into a strand of atoms in a process chillingly called spaghettification. We will grapple with the concept of the event horizon, a point of no return that is less like a physical barrier and more like a one-way door in the fabric of space-time. We will even confront the information paradox, a puzzle that pits the laws of quantum mechanics against the laws of gravity in a conflict that threatens to rewrite fundamental physics. This is not just a list of trivia, this is an exploration of concepts that will fundamentally alter your perspective. To make sense of these mind-bending ideas, we will use relatable analogies. Think of space-time as a stretched rubber sheet. A black hole is like a weight so heavy it creates an infinitely deep well in that sheet. We will break down the science in a way that is accessible, moving from the surprising formation of stellar mass black holes to the supermassive giants that lurk at the centers of galaxies, including our own Milky Way. By the end of this video, the night sky will not look the same. You will understand that it is not a static painting but a dynamic, violent, and breathtakingly beautiful arena where the most extreme events in the universe unfold. So, let's begin our descent into the darkness and illuminate the secrets of black holes. Our very first fact might be the most important one for reshaping your entire perspective, because it addresses a fundamental misconception hidden right in the name. Black holes are not holes. They are not cosmic potholes in the fabric of space that you could accidentally fall into. Instead, think of a black hole as an object, a thing, but one so unimaginably dense that its gravity becomes overpowering. The core of a black hole is a singularity, a point where a tremendous amount of mass has been crushed into a volume of zero size. The laws of physics, as we understand them, break down completely at this point. To visualize this, picture a trampoline representing the fabric of space-time. If you place a marble on it, it creates a small dip. A heavier bowling ball creates a much deeper well. Now imagine taking an object with the mass of several suns and compressing it down to a single, infinitely tiny point. This would create a dip in the trampoline so deep, so infinitely steep, that it forms a pit with sheer walls. Anything that rolls too close to the edge, like a stray marble, will inevitably slide down into the abyss, unable to climb back out. That's the gravitational influence of a black hole. The hole we refer to is actually the event horizon, which is not a physical surface but a boundary in space, the point of no return surrounding this incredible concentration of mass. Once anything, including light, crosses that invisible threshold, it is gone forever from our observable universe, pulled inexorably toward the singularity at the center. So, when you look toward a black hole, you are not looking at an empty hole, but at the shadow cast by the most perfect trap in the universe. This leads us directly to our second astonishing fact, which helps explain how these cosmic monsters fit into the grand architecture of the universe. Black holes are not a one-size-fits-all phenomenon. They come in dramatically different classes, from the relatively common to the truly colossal. Understanding their scale is key to appreciating their role. The first and most familiar type are stellar mass black holes. These are the remnants of massive stars that have lived fast and died young. When a star many times more massive than our Sun exhausts its nuclear fuel, the outward pressure that has supported it against its own immense gravity suddenly vanishes. The core collapses catastrophically, triggering a supernova explosion that blasts the star's outer layers into space. What remains behind, if the core is heavy enough, collapses under its own weight, crushing down past the point of a neutron star and into a black hole. These stellar mass black holes typically contain the mass of about 5 to several dozen suns, all compressed into a region of space perhaps only 20 miles across. A famous example is Cygnus X1, a powerful source of X-rays located about 6,000 light-years away. We can't see the black hole itself, but we can observe its violent effects as it pulls gas from a companion star, heating it to millions of degrees and causing it to glow brilliantly before it vanishes forever. But if stellar mass black holes are impressive, then supermassive black holes are on an entirely different, almost incomprehensible scale. These behemoths are millions or even billions of times more massive than our Sun. They are not the corpses of individual stars, but are thought to have grown over billions of years, likely starting as smaller seeds and devouring vast amounts of gas, dust, and even stars, merging with other black holes along the way. Nearly every large galaxy, including our own Milky Way, harbors one of these supermassive black holes at its very heart. Our local giant is called Sagittarius, a star, a silent titan with a mass equivalent to more than 4 million suns, residing 26,000 light-years away in the direction of the Sagittarius constellation. While it's relatively quiet now, the presence of such a massive object at the galactic center suggests it played a fundamental role in the formation and evolution of the entire galaxy that swirls around it. For a long time, astronomers only knew of these two main categories, creating a puzzling gap. Where were the middleweights? This mystery led to the search for the third-class, intermediate mass black holes. These are theorized to have masses between 100 and 100,000 times that of our Sun. They are thought to be the missing link, the potential seeds from which supermassive black holes grew. Evidence for their existence has been mounting, with observations of unusual star cluster movements and intense bursts of energy that seem too powerful to come from a stellar mass black hole, yet not quite as immense as a supermassive one. Finding these intermediate objects is like discovering a key piece of a cosmic puzzle, helping us understand the life cycle of black holes and their profound influence on the universe from its earliest moments. Now that we understand the different sizes of black holes, let's witness the spectacular and violent birth of the stellar mass variety. This creation story begins not with darkness, but with one of the brightest objects in the cosmos, a massive star. For millions of years, such a star leads a dramatic life, fueled by a constant and precarious battle raging in its core. The immense gravity of the star's own mass is constantly trying to crush it inward. The only thing holding it up is the tremendous outward pressure generated by nuclear fusion, the process of smashing atoms together to create heavier elements and release energy. It's a stable, cosmic tug-of-war, with gravity pulling in and fusion pushing out. This balance, however, is doomed from the start. A star is essentially a giant nuclear furnace, and like any furnace, it eventually runs out of fuel. The star spends its life fusing lighter elements into heavier ones, starting with hydrogen into helium. When the hydrogen is depleted, the core contracts, heats up, and begins fusing helium into carbon and oxygen. This process continues, creating an onion-like structure with heavier elements like neon, magnesium, and silicon forming in successive shells around an increasingly dense core. The final chapter arrives when the core begins fusing silicon into iron. This is the star's last stand. Fusing iron does not release energy, it actually consumes it. In an instant, the supporting outward pressure from fusion vanishes. With the counterforce gone, gravity wins the battle catastrophically. The core, which may be larger than our entire planet, collapses at an astonishing speed in less than a second. This collapse does not go quietly. The outer layers of the star, suddenly without a foundation, come crashing down onto the incredibly dense core and rebound in one of the most energetic events in the universe, a supernova explosion. For a brief period, this single star can outshine its entire host galaxy, scattering newly forged heavy elements like gold, silver, and uranium across space, the very elements that will one day form planets and even life itself. But what of the core? Its fate is sealed by its weight. If the remaining core is between about 1.4 and 2.3 times the mass of our Sun, the collapse is halted by a quantum mechanical force called neutron degeneracy pressure, creating a city-sized neutron star, an unimaginably dense ball of neutrons. However, if the core's mass exceeds approximately 2 to 3 solar masses, no known force in the universe is strong enough to stop the collapse. The crushing weight of over 200,000 Earths worth of material compacted into an area just a few miles across is simply too much. The collapse continues unabated, crushing past the neutron star stage. The matter is compressed into a single point of infinite density, a singularity. The gravitational field around this singularity becomes so intense that it warps space into a closed sphere, creating an event horizon. At that moment, a black hole is born, a permanent shadow where a brilliant star once shone. And at the very center of this newly formed cosmic trap lies the most baffling and mathematically troubling concept of all, the singularity. We've mentioned it before, but what exactly is it? Imagine following the path of that unfortunate marble as it slides down the impossibly steep walls of the trampoline well. It doesn't just stop at the bottom. According to our best understanding of gravity, all that matter, every atom, every particle that crosses the event horizon is pulled toward a single central point. This is the singularity. It's not a physical object you could touch or see. It's a point in space where the black hole's mass is compressed into a volume of zero size. The concepts of density and gravity, as defined by our current laws of physics, cease to have sensible meaning here. They become infinite. To grasp why infinity is such a problem for physicists, think of our scientific laws as a powerful and highly accurate map. Einstein's theory of general relativity is an extraordinary map for the large-scale universe. It perfectly describes how planets orbit stars, how gravity bends light, and how massive objects warp the fabric of space-time. It's the theory that predicted black holes in the first place. But when this map is used to navigate all the way to the singularity, it produces an answer that is physically nonsensical, a point of infinite density. In the real world, infinity is a mathematical concept, not a physical condition. It's a sign that the map has been pushed beyond its limits into a territory where its rules no longer apply. The theory breaks down because it cannot describe a reality where all matter is crushed into a single, dimensionless point. This is where the other great pillar of modern physics must enter the picture, quantum mechanics. While general relativity reigns over the cosmos, quantum mechanics governs the fantastically small world of atoms and subatomic particles. It's a world of probability, uncertainty, and fuzzy boundaries. The problem is that these two theories, our two most accurate and successful maps of reality, are fundamentally incompatible with each other. They speak different mathematical languages and describe the universe in wildly different ways. Under normal circumstances, we can use one for stars and galaxies and the other for particles, and they never have to meet. But the singularity at the heart of a black hole is the one place where the immensely large and the infinitely small are forced to collide. It is a realm where both colossal gravity and subatomic scales exist simultaneously. Therefore, the singularity is not just a strange prediction, it is a glaring signpost pointing toward a deeper truth. It tells us that we are missing a crucial piece of the puzzle, a theory that can seamlessly unite the world of the very large with the world of the very small. Physicists call this sought-after theory quantum gravity. It would be a complete set of laws that work everywhere, from the vast emptiness between galaxies right down to the very center of a black hole. Some theories, like string theory or loop quantum gravity, attempt to solve this problem by proposing that there is no true singularity, that some new quantum effect, perhaps a tremendous outward pressure, prevents matter from collapsing to a point of infinite density. The singularity, then, is the ultimate frontier of theoretical physics. It represents the boundary of human knowledge, a challenge to our deepest understanding of reality, and the key that may one day unlock a unified theory of everything. This brings us to the very boundary of the black hole itself, the defining feature that gives it its name and its terrifying reputation, the event horizon. If the singularity is the black hole's incomprehensible heart, then the event horizon is its point of no return. It's crucial to understand that this is not a solid, physical surface you could bump into like the shell of a planet. Instead, think of it as a mathematical boundary, an invisible sphere in space that marks the final exit door from our universe. Once an object crosses this threshold, the gravitational pull becomes so overwhelming that the velocity required to escape exceeds the speed of light, the ultimate speed limit of the cosmos. Since nothing can travel faster than light, the conclusion is stark and absolute. There is no coming back. The journey across this boundary is a one-way trip into the unknown, and its effects on reality are straight out of science fiction. To visualize this, picture an astronaut on a daring mission, slowly approaching a black hole while their partner remains at a safe distance in a spacecraft. From the perspective of the astronaut falling in, the crossing of the event horizon might not be a dramatic, singular event. There's no flashing sign or physical jolt. If the black hole is large enough, the tidal forces at the event horizon are relatively weak, meaning the astronaut might not even be immediately torn apart. However, their view of the outside universe would become increasingly distorted. The light from the stars behind them would be bent into a narrowing circle of light above, while the darkness below would be absolute. But for their partner watching from the safety of the spaceship, the scene would be utterly bizarre and deeply unsettling. As the astronaut falls toward the event horizon, the incredible gravity would cause a phenomenon known as gravitational time dilation, a key prediction of Einstein's theory of general relativity. Gravity doesn't just warp space, it also warps time. The stronger the gravity, the slower time flows. From the outside observer's viewpoint, the clock on the falling astronaut's suit would appear to tick slower and slower. Their descent would seem to decelerate as they approached the invisible boundary. The astronaut would never actually appear to cross the event horizon. Instead, they would seem to freeze in place, their image becoming progressively redder and dimmer as the light waves struggling to escape lose energy, eventually fading from view entirely over an immense span of time. This creates a profound paradox. For the outside universe, the astronaut's information is seemingly smeared across the surface of the event horizon forever, a ghostly afterimage. But for the astronaut themselves, time passes normally. They would continue their fall, crossing the boundary without a moment's hesitation from their own reference frame, likely meeting their fate at the singularity shortly thereafter. This isn't an illusion. It's a genuine feature of our relativistic universe where the passage of time is not absolute but relative to your gravitational environment. The event horizon, therefore, is not just a physical boundary but also a horizon of causality, a point beyond which no event can ever influence the world outside. It stands as the ultimate cosmic barrier, separating the known from the unknowable. While the event horizon marks the point of no return for light and information, the journey inward is far from gentle. For any object venturing too close, the most immediate and gruesome danger isn't the singularity itself, but the extreme difference in gravity across its own body. This phenomenon has a name as evocative as it is accurate: spaghettification. To understand why this happens, we need to revisit our rubber sheet analogy, but now we'll place a more complex object on it. Imagine that our trampoline has a very steep, deep well representing the black hole. If you drop a soft, stretchy object like a piece of chewing gum near the edge, the part of the gum closest to the well will be pulled down much more strongly than the part farther away. The gum will begin to stretch and thin out, elongating into a stringy line pointing directly toward the center of the well. This is precisely what occurs near a black hole, but with forces of unimaginable power. Gravity weakens with distance according to a simple rule. The force you feel is inversely proportional to the square of your distance from the center. This means that if you are falling feet first toward a stellar mass black hole, your feet are significantly closer to the singularity than your head is. Even a small difference in distance translates into a colossal difference in gravitational pull. Your feet are yanked downward with vastly more force than your torso, which in turn is pulled more strongly than your head. The result is that you are stretched lengthwise as if caught in an ultimate cosmic tug of war. But the stretching is only one part of the equation. At the same time, the sides of your body are being pulled radially inward toward the central axis of your fall. This lateral compression squeezes you from all sides, making you thinner. So you are simultaneously being stretched longitudinally and compressed horizontally. The combination of these tidal forces, the same forces that cause ocean tides on Earth by the Moon's gravity, but amplified to an extreme degree, transforms any object into a long, thin stream of matter. A human being, a spacecraft, or even an entire star would be relentlessly pulled apart, reshaping into a filament of atoms resembling a single strand of spaghetti, spiraling down into the darkness. The size of the black hole plays a dramatic role in your experience. A smaller, stellar mass black hole has a much more compact event horizon and an incredibly steep gravitational gradient. The difference in pull between your head and feet would be catastrophic even from thousands of miles away. You would be spaghettified well before you reached the event horizon, torn apart violently and quickly. A supermassive black hole, however, is a different story. Because its mass is spread over such a vast volume, the event horizon is much farther out, and the gravitational gradient at that boundary is far more gentle. The difference in pull between your head and feet might be negligible at the point of crossing. You could, in theory, pass through the event horizon of a supermassive black hole intact, only to be inevitably stretched and shredded as you journeyed further inward toward the central singularity. This grotesque process is a fundamental consequence of the geometry of space-time around these objects, a stark reminder that the universe operates by laws that are utterly indifferent to our familiar, earth-bound experiences. This brings us to a startling possibility that seems to contradict everything we've just learned about the lethal nature of black holes. While spaghettification is a gruesome and very real fate, it's not an immediate one for every black hole encounter. In fact, there is a theoretical scenario in which an astronaut could cross the event horizon of a black hole and live to tell the tale, at least for a little while. This incredible exception hinges entirely on the black hole's size. Remember, the spaghettification effect is caused by the difference in gravitational pull across an object known as the tidal force. For a small, stellar mass black hole, the event horizon is very close to the singularity, meaning the gravitational gradient is incredibly steep. The difference in pull between your head and your feet would be catastrophic even from a significant distance away. But a supermassive black hole is a different beast altogether. Because its immense mass is spread over such a colossal volume, its event horizon is located much farther out from the central singularity. The radius of the event horizon increases linearly with the black hole's mass. A black hole with the mass of our Sun has an event horizon radius of only about 2 miles. Now consider Sagittarius, a star, the supermassive black hole at our galaxy's center, which has a mass of over 4 million suns. Its event horizon, or Schwarzschild radius, extends over 7 million miles. That's a sphere larger than the orbit of Mercury around our Sun. At this vast distance from the singularity, the gravitational pull is still strong enough to trap light, but the gradient, the change in gravity from one point to another, is much more gentle. The difference in gravitational force between your head and your feet as you cross that boundary could be minuscule, perhaps even less than the force you feel standing on Earth. So, in this purely theoretical exercise, an astronaut piloting a sturdy spacecraft toward a supermassive black hole like Sagittarius, a star, could, in principle, cross the event horizon without being instantly shredded into atomic spaghetti. From their perspective inside the ship, there might be no dramatic physical sensation at the moment of crossing. There is no tangible barrier to hit. The event horizon is a mathematical boundary, not a brick wall. However, their view of the universe would undergo a radical and irreversible transformation. As they crossed this ultimate threshold, the circle of the outside universe they could see through their viewport would rapidly shrink and distort behind them. All paths forward in space now lead inexorably toward the singularity at the center. The concept of away from the black hole ceases to exist. While they would be alive and physically intact, they would have irrevocably left our observable universe. Any light signals they try to send back would simply fall inward with them, unable to climb out. They are now cut off from the rest of existence, sailing into the heart of darkness. This survival, of course, is tragically short-lived. Passing through the event horizon is only the beginning of the end. Once inside, the spacecraft and its occupant are being carried along on a one-way river of spacetime that flows directly toward the singularity. No amount of engine power can change their course. As they continue their journey inward, the tidal forces that were negligible at the horizon begin to intensify. The gravitational pull on the front of the ship becomes noticeably stronger than on the back. Slowly at first, and then with increasing violence, the ship would begin to stretch. The astronaut would feel a gentle tug growing into an irresistible pull. Within a finite amount of time, perhaps minutes or hours depending on the specific black hole, the spaghettification process would begin in earnest, ultimately leading to the same inevitable fate. So, while crossing the horizon might not be immediately lethal, it merely offers a brief, haunting respite, a final glimpse of the cosmos from the most isolated vantage point imaginable before the laws of physics execute their final, crushing verdict. Up until now, we've pictured black holes as perfectly symmetrical, bottomless pits in space-time. But reality is far more dynamic and strange. Most black holes are not static objects. They are cosmic whirlpools spinning at a significant fraction of the speed of light. This rotation fundamentally changes their structure and creates regions of even more bizarre physics. When a massive star collapses to form a black hole, it carries with it the angular momentum from its previous life. Just as an ice skater spins faster when they pull their arms in, the collapsing core of a star spins up to incredible velocities, and this rotation is imprinted on the newborn black hole. The mathematical description for this rotating black hole is known as the Kerr solution, named after the physicist Roy Kerr, and it reveals a far more complex beast than the simpler, non-rotating model. The most dramatic consequence of this spin is the creation of a region outside the event horizon called the ergosphere. Imagine the event horizon as the central point of no return. Now picture a larger, flattened region surrounding it, shaped like a squashed sphere. This is the ergosphere. Within this zone, the black hole's rotation is so violent that it literally drags the fabric of spacetime itself along for the ride. Nothing can stand still here. It's an ultimate cosmic whirlpool where space is flowing faster than the speed of light. You could theoretically fire your rockets to counter the motion, but you would be fighting a losing battle against the current of space-time. The ergosphere is not a point of no return. You can still escape from it if you have enough energy, but it is a point of no stationarity. You are forced to move, caught in the irresistible drag of the rotating black hole. This bizarre property leads to an astonishing theoretical possibility: the extraction of energy from a black hole. The process, known as the Penrose process after physicist Roger Penrose, is a feat of relativistic engineering. Imagine an advanced civilization sending a probe into the ergosphere of a rotating black hole. The probe is designed to split into two pieces at just the right moment. One piece is sent on a trajectory that deliberately falls into the black hole, while the other is programmed to escape. According to the mathematics, the infalling piece can be given a negative energy trajectory. When it crosses the event horizon, it actually reduces the black hole's total mass and rotational energy. To conserve energy, the other fragment that escapes must carry away more energy than the original probe had when it entered. In essence, the black hole has transferred some of its rotational energy to the escaping fragment. While this sounds like science fiction, it has a potential real-world analog observed in the universe: relativistic jets. Many active galactic nuclei, which are powered by supermassive black holes, shoot out colossal beams of radiation and particles at nearly the speed of light, stretching for thousands of light years. It is believed that the intense magnetic fields and the swirling, heated matter in the accretion disk, combined with the rotational energy of the black hole itself, power these incredible jets. The black hole's spin acts like a giant flywheel, and the interaction within the ergosphere helps to launch and collimate these beams, transferring the black hole's rotational energy into a form that can influence the entire galaxy around it. So, rather than being simple drains on the universe, spinning black holes can also be seen as powerful engines, capable of shaping their cosmic environments on a grand scale. This elegant simplicity is perhaps one of the most profound and puzzling facts about black holes. After the violent chaos of a supernova, after a black hole has devoured stars, planets, and vast clouds of gas, you might expect it to be a complex object, retaining some record of its violent history. Yet, according to a fundamental principle in general relativity known as the no-hair theorem, a black hole is astonishingly simple. It is said to have no hair, a metaphor meaning it has no unique, distinguishing features or complicated structure. Once a black hole settles into a stable state, which happens very quickly after its formation, it can be completely and uniquely described by just three, and only three, properties: its mass, its electric charge, and its angular momentum or spin. Think of it this way: if you want to describe a common object like a car, you need a long list of details: its color, its model, the number of doors, the material of its seats, the scratches on its bumper, its license plate number. Each car is unique because it carries a vast amount of information about itself and its history. A black hole, in stark contrast, is the ultimate minimalist. It doesn't matter if it was formed from a star made mostly of hydrogen or one rich in iron. It doesn't matter if it just swallowed a diamond planet or a helium-rich gas cloud. All of those intricate details, the chemical composition, the atomic structure, the number of things it consumed, are utterly obliterated and lost. The only things that remain for an outside observer to measure are the total mass, which determines the size of its event horizon, its net electric charge, which is typically negligible as black holes tend to be electrically neutral, and its spin, which shapes the ergosphere. That's it. Everything else is hidden behind the event horizon, permanently inaccessible. This leads us directly to one of the most significant and heated debates in modern physics: the black hole information paradox. The no-hair theorem, a consequence of Einstein's classical general relativity, seems to violate a fundamental tenet of quantum mechanics, the principle of unitarity. In the quantum world, information can never be truly destroyed. It can be scrambled, transformed, or made incredibly difficult to read, but it must, in principle, be preserved. For example, if you burn a book, the information contained in the letters seems lost, but a hypothetical super-intelligent being could, in theory, collect every single particle of smoke and ash, measure their states and trajectories with infinite precision, and reverse the process to reconstruct the original book. The information was never destroyed, it was just transformed into a vastly more complex state. Now, apply this to a black hole. When an object falls in, the no-hair theorem suggests that all the intricate information about that object, the specific arrangement of atoms that made it a book or a star or an astronaut, is irretrievably lost, erased from the universe. Only the three simple numbers of mass, charge, and spin are added to the black hole. This creates a direct conflict. General relativity, with its no-hair theorem, says the information is gone forever. Quantum mechanics insists it cannot be. Both theories are incredibly well-tested and successful in their own domains, yet they provide contradictory answers for what happens to information inside a black hole. This is the core of the paradox, and it suggests that our understanding of physics is fundamentally incomplete, particularly where gravity and quantum mechanics meet. The potential resolution to this paradox has evolved dramatically over the decades, largely driven by the work of Stephen Hawking. He discovered that black holes are not entirely black. Due to quantum effects occurring just outside the event horizon, black holes can slowly radiate energy away in the form of particles, a phenomenon now known as Hawking radiation. This leads to the astonishing conclusion that black holes can evaporate over immense timescales, but this only deepens the information problem. The Hawking radiation predicted by early calculations seemed to be purely thermal, like the heat from a stove. It contained no specific information about what fell into the black hole. So if a black hole evaporates completely, disappearing from the universe, what happened to all the information about the things it consumed? Was it truly lost, violating quantum mechanics, or is it somehow encoded in the Hawking radiation in a way we don't yet understand? The search for an answer to this question continues to drive theoretical physics forward, pushing the boundaries of our knowledge and forcing us to confront the very nature of reality, information, and the fabric of spacetime itself. This conflict between the foundational laws of physics brings us to the work of one of the most celebrated scientists of the 20th century, Stephen Hawking. In the 1970s, Hawking applied the strange rules of quantum mechanics to the space just outside a black hole's event horizon, and he made a discovery that shocked the scientific community. Black holes are not completely black. They glow, they emit a faint, ghostly radiation, now famously known as Hawking radiation. This revelation was monumental because it suggested that black holes have a temperature and therefore are not eternal. They can slowly evaporate over astronomical timescales. To grasp how this seemingly impossible phenomenon occurs, we need to venture into the bizarre quantum world. Empty space, according to quantum field theory, is not truly empty. It is a seething, frothing sea of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence out of nothing, borrowing energy from the vacuum for an incredibly brief moment before annihilating each other and returning the energy, following the strict rules of quantum uncertainty. This constant, frantic activity happens everywhere, all the time. Normally, these pairs vanish without a trace almost instantly, but something extraordinary happens when this quantum fluctuation occurs right at the edge of a black hole's event horizon. Imagine one of these virtual particle pairs appearing just outside the point of no return. In an incredibly rare but possible event, one particle of the pair might fall across the event horizon, while its partner manages to escape outward into space. The particle that falls in has negative energy, which effectively reduces the mass of the black hole by a tiny amount. Its partner, now severed from its other half and unable to annihilate, becomes a real particle carrying positive energy away from the black hole. To an outside observer, it appears as though the black hole has just emitted a particle. This is Hawking radiation. It's not radiation coming from inside the black hole. Rather, it is radiation created by the black hole's gravitational energy at its very boundary. The implications of this are staggering. A black hole is continuously losing mass through this process. For a typical stellar mass black hole, the temperature of this radiation is minuscule, far colder than the background temperature of the universe, meaning it absorbs more energy from cosmic microwave background radiation than it emits. Its evaporation is effectively on pause, but over time, as the universe expands and cools, the balance will shift. A black hole will begin to lose mass, and as it gets smaller, a fascinating feedback loop kicks in. A smaller black hole has a smaller event horizon, which increases the curvature of space at its boundary. This makes it easier for more virtual particle pairs to be separated, which increases the rate of Hawking radiation. The black hole evaporates faster and faster as it shrinks, until in a final burst of energy, it is predicted to vanish completely. And this is where Hawking's discovery magnified the information paradox into a full-blown crisis. The Hawking radiation that he initially calculated was purely thermal, like the glow from a hot piece of coal. It was random and featureless. It contained no specific information whatsoever about the intricate details of the books, stars, and astronauts that had fallen in over the eons. If a black hole evaporates entirely, leaving behind only this thermal radiation, then all the information about everything it ever consumed appears to be permanently erased from the universe. This is the core of the black hole information paradox, the irreconcilable conflict between the deterministic, information-preserving laws of quantum mechanics and the information-destroying prediction of a black hole's final evaporation according to Hawking's original calculations. The physics community has been grappling with this paradox for decades, and potential resolutions have sparked fierce debate. One prominent line of thinking suggests that the information is not actually lost. Perhaps it is somehow encoded on the event horizon itself, like a giant cosmic hologram. The holographic principle proposes that all the information about what falls into a black hole is preserved on its two-dimensional surface area, and then slowly, and in an incredibly scrambled form, radiated back out via the Hawking radiation over the black hole's immense lifetime. Another possibility is that black holes don't completely vanish. Maybe they leave behind a tiny, stable remnant, a plank-sized fossil that contains all the compressed information of everything that fell in. However, this idea has its own set of problems, as such a remnant would have to hold an infinite amount of information. The consensus among many theoretical physicists today is leaning toward the idea that information is in fact preserved. Stephen Hawking himself eventually came around to this view, conceding in 2004 that information probably does escape, albeit in a highly corrupted form. The challenge is that decoding that information from the Hawking radiation would be a task of unimaginable complexity, like reconstructing a burned book from the precise pattern of the smoke particles. The information paradox remains one of the most profound unsolved problems in fundamental physics, a stark reminder that at the edge of our understanding, the universe still holds deep mysteries that challenge our most cherished scientific principles. This conflict between the foundational laws of physics brings us to the work of one of the most celebrated scientists of the 20th century, Stephen Hawking. In the 1970s, Hawking applied the strange rules of quantum mechanics to the space just outside a black hole's event horizon, and he made a discovery that shocked the scientific community. Black holes are not completely black. They glow, they emit a faint, ghostly radiation, now famously known as Hawking radiation. This revelation was monumental because it suggested that black holes have a temperature and therefore are not eternal. They can slowly evaporate over astronomical timescales. To grasp how this seemingly impossible phenomenon occurs, we need to venture into the bizarre quantum world. Empty space, according to quantum field theory, is not truly empty. It is a seething, frothing sea of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence out of nothing, borrowing energy from the vacuum for an incredibly brief moment before annihilating each other and returning the energy, following the strict rules of quantum uncertainty. This constant, frantic activity happens everywhere all the time. Normally, these pairs vanish without a trace almost instantly, but something extraordinary happens when this quantum fluctuation occurs right at the edge of a black hole's event horizon. Imagine one of these virtual particle pairs appearing just outside the point of no return. In an incredibly rare but possible event, one particle of the pair might fall across the event horizon, while its partner manages to escape outward into space. The particle that falls in has negative energy, which effectively reduces the mass of the black hole by a tiny amount. Its partner, now severed from its other half and unable to annihilate, becomes a real particle carrying positive energy away from the black hole. To an outside observer, it appears as though the black hole has just emitted a particle. This is Hawking radiation. It's not radiation coming from inside the black hole. Rather, it is radiation created by the black hole's gravitational energy at its very boundary. The implications of this are staggering. A black hole is continuously losing mass through this process. For a typical stellar mass black hole, the temperature of this radiation is minuscule, far colder than the background temperature of the universe, meaning it absorbs more energy from cosmic microwave background radiation than it emits. Its evaporation is effectively on pause, but over time, as the universe expands and cools, the balance will shift. A black hole will begin to lose mass, and as it gets smaller, a fascinating feedback loop kicks in. A smaller black hole has a smaller event horizon, which increases the curvature of space at its boundary. This makes it easier for more virtual particle pairs to be separated, which increases the rate of Hawking radiation. The black hole evaporates faster and faster as it shrinks, until in a final burst of energy, it is predicted to vanish completely. And this is where Hawking's discovery magnified the information paradox into a full-blown crisis. The Hawking radiation that he initially calculated was purely thermal, like the glow from a hot piece of coal. It was random and featureless. It contained no specific information whatsoever about the intricate details of the books, stars, and astronauts that had fallen in over the eons. If a black hole evaporates entirely, leaving behind only this thermal radiation, then all the information about everything it ever consumed appears to be permanently erased from the universe. This is the core of the black hole information paradox, the irreconcilable conflict between the deterministic, information-preserving laws of quantum mechanics and the information-destroying prediction of a black hole's final evaporation according to Hawking's original calculations. The physics community has been grappling with this paradox for decades, and potential resolutions have sparked fierce debate. One prominent line of thinking suggests that the information is not actually lost. Perhaps it is somehow encoded on the event horizon itself, like a giant cosmic hologram. The holographic principle proposes that all the information about what falls into a black hole is preserved on its two-dimensional surface area, and then slowly, and in an incredibly scrambled form, radiated back out via the Hawking radiation over the black hole's immense lifetime. Another possibility is that black holes don't completely vanish. Maybe they leave behind a tiny, stable remnant, a plank-sized fossil that contains all the compressed information of everything that fell in. However, this idea has its own set of problems, as such a remnant would have to hold an infinite amount of information. The consensus among many theoretical physicists today is leaning toward the idea that information is in fact preserved. Stephen Hawking himself eventually came around to this view, conceding in 2004 that information probably does escape, albeit in a highly corrupted form. The challenge is that decoding that information from the Hawking radiation would be a task of unimaginable complexity, like reconstructing a burned book from the precise pattern of the smoke particles. The information paradox remains one of the most profound unsolved problems in fundamental physics, a stark reminder that at the edge of our understanding, the universe still holds deep mysteries that challenge our most cherished scientific principles. While we have been exploring the dramatic life cycles of stars, there is another, more ancient and elusive type of black hole that may be hiding in the cosmos, a relic from the very dawn of time itself. These are known as primordial black holes, and they present a fascinating alternative to the stellar formation story. Unlike the black holes born from the death of massive stars, primordial black holes are thought to have formed not from the collapse of matter, but from the collapse of space itself in the incredibly dense and chaotic environment just moments after the Big Bang. To understand how this could happen, we need to travel back to the universe's first second of existence. In this initial fiery fraction of a moment, the entire cosmos was an unimaginably hot, dense, and turbulent soup of energy and fundamental particles. There were no stars, no galaxies, not even atoms. According to cosmological theories, the density of the universe during this epoch was not perfectly smooth. There were tiny, random fluctuations. Some regions were ever so slightly denser than others. In most areas, the rapid expansion of the universe smoothed these fluctuations out. But in regions where the density was exceptionally high, gravity could have overcome the expansion. A pocket of space could have become so overdense that its own gravity caused it to collapse directly into a black hole without ever needing a star to form and die first. It would be a black hole born from a knot in the fabric of space-time. This unique origin story leads to one of the most intriguing possibilities about primordial black holes. They could theoretically exist in a vast range of sizes. A stellar mass black hole is constrained by the mass of the star that formed it, but a primordial black hole could be almost any mass. It could be as small as an asteroid, with the mass of a mountain compressed into a space smaller than an atom. Or it could be a monster larger than 1,000 suns. Their size would depend entirely on the scale of the density fluctuation that spawned them. A small patch of high density would create a tiny black hole. A larger, region-wide fluctuation could create a supermassive one. This opens up the extraordinary idea that the supermassive black holes we see at the centers of galaxies today might not have grown slowly over time. Some could have been born large, as primordial seeds already in place when the first stars began to shine. This brings us to the most compelling reason scientists are so interested in these hypothetical objects. They are a leading candidate for dark matter. We know that about 85% of the matter in the universe is dark matter. It exerts gravitational pull, but it does not emit, absorb, or reflect light, making it completely invisible to our telescopes. The nature of dark matter is one of the biggest mysteries in all of science. If a significant portion of primordial black holes were created with masses similar to that of a large asteroid or a small planet, they could be scattered throughout the universe, including in the vast halos surrounding galaxies. They would be invisible, yet their collective gravity would perfectly explain the observed rotation of galaxies and the bending of light by galaxy clusters, the very evidence that led us to propose dark matter in the first place. They would be a simple, elegant solution. Dark matter could just be made of ancient black holes. However, despite decades of searching, no primordial black hole has ever been conclusively detected. The hunt for them is a masterclass in scientific ingenuity, relying on indirect methods. One of the most promising techniques involves a phenomenon called gravitational microlensing. If a primordial black hole were to pass directly between Earth and a distant star, its gravity would act like a lens, bending and focusing the star's light. From our perspective, the star would temporarily appear to brighten. By monitoring millions of stars in nearby galaxies like the Large Magellanic Cloud, astronomers have searched for these characteristic flashes. So far, the results have largely ruled out primordial black holes in a specific mass range, particularly those around the mass of a large planet, as being the primary component of dark matter. But the search continues, with other methods looking for the ripples in spacetime they might create as they merge, or the subtle effects they might have on the cosmic microwave background, the afterglow of the Big Bang. The mystery of primordial black holes remains wide open, a tantalizing possibility that connects the first instant of creation to the invisible scaffolding of the cosmos we observe today. This intricate dance between a supermassive black hole and its host galaxy leads us to one of the most significant discoveries in modern astrophysics, a finding that hints at a deep, fundamental connection. For a long time, astronomers viewed the central black hole as just another feature of a galaxy, perhaps a dangerous relic of its formation. But then, around the turn of the millennium, researchers began to notice a surprising pattern, a cosmic correlation that was too precise to be a coincidence. They found that the mass of a galaxy's central supermassive black hole is directly proportional to the mass of the galaxy's central bulge, the dense, spherical collection of older stars at its core. The relationship is remarkably tight. In galaxies without a significant bulge, like some spiral galaxies, the central black hole tends to be relatively small. But in galaxies with a massive, prominent bulge, the black hole is invariably a true behemoth. This correlation is stunning because the scales involved are so vastly different. The black hole itself, for all its immense gravity, is an infinitesimally small speck compared to the galaxy it inhabits. Its event horizon is a tiny dot on the galactic map. The bulge, on the other hand, contains billions of stars spread across thousands of light years. For these two vastly different structures to have their masses so closely linked, they cannot have evolved independently. They must have grown together, their fates intertwined over billions of years. It's as if the growth of the city was mysteriously tied to the size of a single, specific pebble lying in the main town square. This discovery strongly suggests a process of co-evolution, a symbiotic relationship where the galaxy and its central black hole influence each other's development. The leading theory for how this happens involves the black hole's active phases, periods when it is furiously consuming matter. As vast amounts of gas and dust spiral inward, they form an incredibly hot, bright accretion disk, turning the black hole into an active galactic nucleus, one of the most powerful energy sources in the universe. During this feeding frenzy, the system doesn't just release light, it can also generate colossal outflows of energy. These come in two main forms: powerful particle jets shooting out from the poles at near light speed, and immense winds of radiation and gas blowing outward from the accretion disk. This outpouring of energy acts as a cosmic feedback mechanism. The tremendous heat and pressure from the active black hole can blow away the surrounding reservoirs of cold gas, the very raw material needed to form new stars. By heating the galactic core and disrupting star-forming clouds, the black hole effectively puts a brake on star formation in the central region of the galaxy. It regulates its own growth and the growth of the galactic bulge. If the black hole grows too massive too quickly, its violent outbursts can shut down the gas supply, starving both itself and the surrounding region of new stars. This self-regulating cycle creates a natural balance, explaining why more massive bulges have more massive black holes. They grew in lockstep with the black hole's activity, periodically quenching star formation, ensuring that the bulge and the black hole didn't grow out of proportion to one another. This feedback process is not just a theoretical idea. We see evidence of it in the universe today. In some galaxy clusters, astronomers observe vast cavities or bubbles carved out in the million-degree gas that fills the space between galaxies. These cavities are precisely aligned with the jets shooting from the central galaxy's supermassive black hole. The energy required to create these enormous bubbles is staggering. demonstrating that black hole feedback is a dominant force, capable of influencing not just its own galaxy, but the entire surrounding intergalactic environment. By pumping energy into the system, the black hole prevents the hot gas from cooling down and falling back into the galaxy to form new stars, effectively keeping the entire galaxy cluster in a stable but relatively quiet state. This reveals the supermassive black hole not as a silent monster, but as an active governor, a cosmic thermostat that has played a pivotal role in shaping the large-scale structure of the universe we see today. But for all their governing power, a quiet supermassive black hole is just one state of being. When these cosmic giants awaken and begin to feast, they can transform into the most luminous and violent objects in the entire universe. These are quasars, a name derived from quasi-stellar radio source, and they represent the ultimate expression of a black hole's power. When astronomers first detected quasars in the 1950s and 60s, they were baffled. They appeared as pinpricks of light like distant stars, but their spectra revealed something impossible. They were moving away from us at tremendous speeds, meaning they were not only incredibly far away but also blindingly bright. A single quasar can outshine the combined light of every single star in its host galaxy, and can be seen from over 10 billion light-years away, acting as a lighthouse beam from the early universe. This phenomenal energy output has one source, the supermassive black hole's accretion disk. A quasar is born when a black hole finds itself in an environment rich with gas, dust, and even entire stars. As this matter is pulled in by the black hole's immense gravity, it doesn't fall straight in. Instead, it forms a rapidly spinning, flattened disk around the event horizon, much like water swirling down a drain. The particles within this disk rub against each other at fantastic speeds, creating immense friction and heating the material to temperatures of millions of degrees. At these extremes, the matter glows with a fierce, intense light across the entire electromagnetic spectrum, from X-rays to visible light. The conversion of gravitational energy into radiation is incredibly efficient, far more so than nuclear fusion. This is why a region of space not much larger than our solar system can outshine a galaxy containing hundreds of billions of stars. The light from a quasar is so brilliant that it can drown out our view of its host galaxy, making the galaxy itself invisible against the glare of its own core. But quasars are more than just luminous. They are often accompanied by another dramatic feature, relativistic jets. These are colossal, narrow beams of ionized matter that shoot out from the poles of the black hole's accretion disk at velocities approaching the speed of light. These jets can extend for hundreds of thousands of light years, far beyond the boundaries of the host galaxy. The mechanism that creates these jets is thought to involve the black hole's powerful magnetic fields, which get wound up by the rotating accretion disk, funneling some of the infalling material outward along the axis of rotation. When one of these jets is pointed nearly directly at Earth, the object is called a blazar, and its brightness can vary wildly and rapidly, providing astronomers with crucial clues about the extreme physics happening near the event horizon. Quasars are not a permanent feature of a galaxy's life. They represent a relatively brief, albeit spectacular, phase in its evolution, a teenage growth spurt of cosmic proportions. This active phase is thought to last for perhaps 100 million to 1 billion years, a long time by human standards, but just a fraction of the galaxy's total life. During this time, the black hole consumes matter at a ferocious rate, growing rapidly in mass and unleashing enough energy to influence the entire galaxy. Eventually, the quasar phase ends when the black hole consumes most of the available fuel in its immediate vicinity. The feeding frenzy slows, the brilliant accretion disk dims, and the quasar transforms into a quiet, supermassive black hole like the one at the center of our own Milky Way. The discovery of quasars was therefore a monumental step in understanding the life cycle of galaxies. revealing that the silent titans we see today were once the brilliant, dominant beacons that lit up the early cosmos. Moving from the theoretical brilliance of quasars to a tangible, breathtaking reality, the year 2019 marked a historic milestone in our quest to understand these cosmic enigmas. For the first time in human history, we were able to look directly into the abyss. The Event Horizon Telescope collaboration did not just detect a black hole, it captured an image of its shadow, providing the most direct visual evidence of their existence and confirming a prediction made by Albert Einstein over a century earlier. This was not a photograph in the traditional sense, but a computational masterpiece painstakingly reconstructed from data collected by a virtual telescope the size of our entire planet. The target of this monumental effort was the supermassive black hole at the heart of the galaxy Messier 87, or M87, a colossal giant 55 million light-years away with a mass 6.5 billion times that of our Sun. Its immense size and relative proximity made it a perfect candidate. However, capturing its image presented an almost insurmountable challenge. From our vantage point, the black hole's event horizon is incredibly tiny in the sky, like trying to photograph a donut on the surface of the moon. No single telescope on Earth possesses the resolving power to see such a minute detail. The ingenious solution was to link radio observatories from across the globe, from the high deserts of Chile to the volcanic peaks of Hawaii and the frigid landscapes of the South Pole, creating a planet-sized interferometer known as the Event Horizon Telescope. By synchronizing these telescopes using atomic clocks, astronomers could effectively simulate a single dish as wide as Earth, achieving the resolution necessary to peer into the heart of M87. The now iconic image, a fiery orange ring of light encircling a dark central shadow, is a perfect illustration of extreme gravity in action. That brilliant ring is not the event horizon itself, but something even more fascinating, the photon sphere or the accretion disk. The dark central region is the black hole's shadow, a window into the event horizon. Here's how it works. The black hole is surrounded by a superheated accretion disk of glowing gas. The light from this disk travels toward us, but the black hole's immense gravity acts like a lens, bending the paths of the light rays in a process called gravitational lensing. The light that passes just above the black hole gets bent around it, while the light that comes from directly behind the black hole is bent so severely that it forms a bright ring. The light that ventures too close, however, crosses the event horizon and is lost forever. This creates a distinct shadow, a dark void at the center of the ring that is about 2.5 times larger than the actual event horizon. This image was a triumphant validation of Einstein's theory of general relativity. The size and shape of the shadow matched the predictions of his equations with remarkable precision. In a universe governed by his description of gravity, a black hole's shadow should be almost perfectly circular. The image of M87 revealed just that, a circular shadow, confirming that we are observing a spinning black hole described by the Kerr solution. It ruled out several alternative theories of gravity that predicted different shadow shapes. For scientists, this was not just a pretty picture. It was a critical test of our fundamental understanding of physics under the most extreme conditions imaginable. It transformed black holes from abstract mathematical concepts, supported by indirect evidence, into observable celestial objects that we can now study in detail, opening a new window onto the most violent and energetic processes shaping our universe. While we have marveled at the image of a black hole millions of light years away, we don't need to look to the distant cosmos to find one of these monsters. A silent titan resides right in our own cosmic backyard, at the very heart of the Milky Way galaxy. This is Sagittarius, a star, the supermassive black hole that anchors our home galaxy, and its story is one of the most compelling detective stories in modern astronomy. For decades, its existence was a strong suspicion based on indirect evidence, but it wasn't until we began tracking the frantic dance of stars around an invisible point that we could truly prove, beyond a reasonable doubt, that a colossal, dark object was lurking there. The journey to confirm Sagittarius, a star's identity, required patience and incredible precision. Astronomers used powerful telescopes like the Keck Observatory in Hawaii and the Very Large Telescope in Chile to observe the galactic center for over 2 decades. Their targets were a group of stars known as the S-stars, which orbit perilously close to the galactic center. By taking painstaking measurements year after year, they were able to map the precise paths of these stars. What they found was astounding. These stars were not moving in slow, stately orbits. They were whipping around an invisible focal point at speeds exceeding 3,000 miles per second. One star, known as S2, completes a full orbit in just 16 years, a blink of an eye in cosmic terms. Its orbit is a highly elongated ellipse that brings it breathtakingly close to the unseen mass. This stellar motion provided the smoking gun. By applying the same laws of gravity that govern the orbits of planets around our Sun, astronomers could calculate the mass responsible for hurling these stars around at such incredible velocities. All of that immense gravitational influence was coming from a region of space smaller than our solar system. The math was unequivocal. Confined within that tiny volume was a mass equivalent to more than 4 million suns. The only known object in the universe that can pack so much mass into such a small space is a supermassive black hole. This was not just circumstantial evidence, it was a direct measurement of the black hole's gravitational signature, the most compelling proof possible short of a direct image. Then, in 2022, the Event Horizon Telescope collaboration delivered that very image, giving us a face for the monster at our galaxy's center. The achievement was, in some ways, even more impressive than the image of M87's black hole. While Sagittarius, a star, is much closer to us, it is also significantly smaller and less active. Its appetite is currently modest, meaning its accretion disk is fainter and more variable, like a flickering fire compared to the brilliant blaze of M87. Capturing its image was like trying to photograph a donut that's rapidly changing shape and brightness. The team had to develop sophisticated new algorithms to piece together the data, effectively creating a family photo from the flickering glimpses they collected. The resulting image, a glowing ring of light with a dark central shadow, confirmed everything the stellar orbits had told us. It provided a direct visual confirmation of the supermassive black hole whose presence we had inferred from its gravitational pull. Seeing the shadow of Sagittarius, a star, made it real in a profound new way. This is not an abstract concept in a distant galaxy. It is the gravitational anchor of our own spiral home, a silent force that has shaped the Milky Way's evolution over billions of years. Its relative calm today belies a potentially violent past, and its presence reminds us that even our own quiet corner of the universe is governed by the same extreme physics that power the most energetic objects in the cosmos. But for all the power of our telescopes to capture light, there was an entire symphony of cosmic events happening in complete darkness, entirely invisible to us. That changed forever on September 14, 2015, when humanity gained a new sense, the ability to hear the universe. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a fleeting, almost imperceptible ripple in the very fabric of spacetime. This ripple was a gravitational wave, and it was generated by an event of cataclysmic power, the final death spiral and merger of two black holes over 1 billion light-years away. This wasn't just a new discovery, it was the opening of an entirely new window on the cosmos, allowing us to observe the universe through the medium of gravity itself. To understand what LIGO heard, we need to revisit Einstein's concept of spacetime. Imagine spacetime as the calm, still surface of a pond. If you gently place a bowling ball on the surface, it creates a deep depression, warping the surface around it. This is analogous to a massive object like a star or black hole warping space-time with its gravity. Now, if you were to take two bowling balls and spin them around each other on the surface of the pond, they wouldn't just sit there, they would create ripples that propagate outward across the water. In exactly the same way, when two massive, dense objects like black holes or neutron stars orbit each other, they don't just sit in their gravitational wells. Their violent motion sends out ripples in space-time, which are gravitational waves. These waves are not made of matter, they are traveling distortions of space itself, stretches and squeezes that travel outward at the speed of light. The signal that LIGO detected was the final frantic moments of a black hole merger. For billions of years, these two black holes had been orbiting each other, slowly losing energy by emitting gravitational waves and inching closer together. In the last few seconds, their dance became a deadly embrace. They spiraled inward at a significant fraction of the speed of light, their orbits tightening rapidly. The frequency and amplitude of the gravitational waves they emitted increased dramatically, creating a characteristic signal that scientists call a chirp. This chirp is a sound that can be translated into an audible frequency, and it captures the entire story: the increasing tempo of the orbit, the final merger where the two black holes became one, and the ring down as the newly formed single black hole settled into a stable, quiet sphere, vibrating like a struck bell until the ripples faded away. Detecting these incredibly faint ripples is a feat of almost unbelievable engineering. A gravitational wave passing through Earth stretches space in one direction and squeezes it in the perpendicular direction. The LIGO observatories are designed to measure this minuscule distortion. Each facility consists of two 4-kilometer-long arms arranged in an L shape. A laser beam is split and sent down each arm, bouncing off mirrors at the ends to travel back and recombine. When a gravitational wave passes through, it changes the length of one arm relative to the other by an amount thousands of times smaller than the diameter of a proton. This tiny change alters how the laser beams recombine, creating an interference pattern that reveals the passage of the wave. To rule out local vibrations like earthquakes or even passing trucks, two identical detectors operate in unison, one in Louisiana and one in Washington state. A real gravitational wave will hit both detectors with a time delay consistent with the speed of light. The Virgo Observatory in Italy adds a third point, allowing scientists to triangulate the direction of the source in the sky. The implications of this new sense of hearing are profound. Before gravitational wave astronomy, our view of the universe was based entirely on light, from radio waves to gamma rays. But many of the most violent events, like the merger of two black holes, are completely dark. They emit no light whatsoever. Gravitational waves are the only way to directly observe them. The first detection confirmed a 100-year-old prediction of general relativity and provided the most direct evidence yet for the existence of black holes. It also revealed a population of stellar mass black holes that we didn't know existed, some with masses larger than theorists thought possible. Each new chirp from the cosmos adds a new data point, helping us build a census of black holes and neutron stars, understanding how they form, and testing the laws of gravity under the most extreme conditions imaginable. We are no longer just stargazers. We have become listeners to the subtle rhythms of space-time, hearing the echoes of collisions that shape the invisible architecture of the universe. Even the title of supermassive, which encompasses the 4 million solar mass giant at our galaxy's center, fails to capture the true scale of the most monstrous black holes in the cosmos. Beyond the supermassive lies a category so immense it requires a new term, ultramassive. These are the leviathans of the universe, black holes with masses not of millions, but of tens of billions of times that of our sun. Their existence pushes the boundaries of what we thought was possible and challenges our understanding of galactic evolution. A prime example of such a behemoth resides at the heart of the galaxy home 15A, which lies at the center of a galaxy cluster about 700 million light-years away. The black hole there is not just large, it is staggeringly colossal, with a mass measured at a staggering 40 billion times the mass of our Sun. To put that almost incomprehensible scale into perspective, its event horizon would be larger than our entire solar system, extending well beyond the orbit of Pluto. The sheer size of these ultramassive black holes presents a fascinating puzzle for astronomers. How did they grow so large so quickly? A stellar mass black hole forms from a single star, and a typical supermassive black hole grows over billions of years by steadily consuming gas and merging with other black holes. But to reach tens of billions of solar masses, a more extreme history is required. The leading theory points to a violent and relentless series of cosmic mergers. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies. At the center of the most massive clusters sits a dominant central galaxy, often a giant elliptical galaxy that has grown fat by cannibalizing its smaller neighbors. Home 15 is the quintessential cannibal galaxy. Over the eons, it has likely consumed numerous smaller galaxies, and with each galactic merger, the supermassive black holes at their centers would have eventually spiraled together and merged. This process creates a kind of black hole dynasty. With each merger, the central black hole gains a massive infusion of mass, growing larger and more powerful. In the dense environment of a galaxy cluster, this cycle of galactic cannibalism and black hole merger can repeat itself again and again. The central black hole effectively sits at the top of the galactic food chain, feasting on a steady diet of its rivals. There is also speculation that some of these ultramassive black holes could be primordial in nature, born exceptionally large in the universe's infancy, giving them a head start that allowed them to accumulate even more mass over time. However, the relentless merger scenario within the crowded cores of galaxy clusters remains the most widely accepted explanation for these gravitational titans. Their immense size is a direct testament to the most violent and dramatic events in cosmic history, a chronicle of conquest written in the language of gravity. Our journey through the cosmos has so far focused on black holes firmly anchored in place, whether at the hearts of galaxies or in stable binary systems. But the galaxy holds another, more ghostly secret. Not all black holes stay where they are born. Some are cosmic drifters, cast out from their stellar nurseries to roam the interstellar darkness alone. These are rogue black holes, invisible nomads wandering the vast expanse of the Milky Way, and their existence adds a chilling, almost cinematic dimension to the galaxy's hidden population. The journey to becoming a rogue begins with the very event that creates a stellar mass black hole, the supernova explosion. While we often picture a supernova as a perfectly symmetrical blast, the reality is far more chaotic. These stellar deaths can be profoundly asymmetric. Imagine a massive star in its final moments. As its core collapses, the ensuing explosion may not happen evenly in all directions. Instabilities can cause the supernova to kick more powerfully in one direction, like a natural rocket engine. If this kick is strong enough and directed in just the right way, it can literally propel the newborn black hole, sending it hurtling out of its birthplace at speeds of hundreds of thousands of miles per hour. This is similar to the process that gives neutron stars their high velocities, creating what are known as pulsar kick velocities, and for a black hole, the effect can be just as dramatic, ejecting it from its native star cluster or galactic neighborhood. There is another, even more dynamic way a black hole can be sent wandering. Imagine a dense star cluster, a crowded metropolis of stars where gravitational encounters are frequent and violent. In such an environment, black holes, being the most massive objects, will naturally sink toward the center of the cluster through a process called dynamical friction. This creates a dense core where multiple black holes can interact. When two black holes form a binary system and a third star or black hole passes too close, a complex gravitational dance can occur. Through a process known as a three-body interaction, the least massive object in the encounter can be flung outward at tremendous speed, effectively ejected from the cluster entirely. In some cases, the black hole itself becomes the projectile, cast out into the galactic halo to begin an eternal journey through empty space. Detecting these dark wanderers is one of astronomy's greatest challenges. A lone black hole drifting in the void between stars emits no light and has no companion star to strip material from. It is, for all practical purposes, completely invisible. However, Einstein's theory of general relativity provides us with a single, delicate method to find them: gravitational microlensing. The principle is elegant. As a rogue black hole travels through the galaxy, its immense gravity warps the space around it, creating a temporary lens. If this invisible lens passes directly between Earth and a distant background star, it will bend and focus the star's light. From our perspective, the star will appear to temporarily brighten, becoming magnified for a period that can last from a few hours to several months, depending on the mass of the black hole and the geometry of the event. This microlensing event is a fleeting astronomical signature. The brightening is symmetric. The star's light curve rises smoothly to a peak and then fades away as the black hole moves past our line of sight. By carefully monitoring millions of stars in dense fields, such as toward the galactic bulge, astronomers can search for these characteristic, unseen lens events. Distinguishing a black hole lens from a more common object like a faint star or a brown dwarf requires precise measurements. The key is in the duration of the event and the amount of light bending, which is related to the lens's mass. A long-duration event with significant lensing but no visible object points strongly to a massive dark lens, a prime candidate for a rogue black hole. In recent years, analyzers of data from projects like the Optical Gravitational Lensing Experiment and the Hubble Space Telescope have provided compelling evidence for a handful of these solitary black holes, suggesting that there could be a substantial population of them silently moving among the stars. The idea that such profound darkness could be drifting unseen through our galaxy forever changes our perception of the interstellar medium from empty space to a landscape populated by ancient wandering ghosts. But the ability to hear the collisions of black holes and witness their shadows is just the beginning of how these objects warp our understanding of reality. They may even hold the key to a concept that has long been the domain of science fiction: time travel. According to the strict mathematics of Einstein's theory of general relativity, the intense gravitational fields around black holes don't just bend space, they twist time into knots. In particular, a specific type of black hole could, in theory, function as a natural time machine. This possibility arises from a solution to Einstein's equations for a rotating black hole, which we've already encountered with the ergosphere. Within this complex geometry, physicists have found that it might be possible for paths through spacetime to loop back on themselves. These hypothetical pathways are known as closed time-like curves. To grasp what a closed time-like curve is, we first need to understand how physicists view the universe. Spacetime is a four-dimensional fabric combining the three dimensions of space with the one dimension of time. Any object's path through spacetime is called its world line. For us, and for every object in the universe, this world line always moves forward in time. We are carried from the past toward the future at a steady rate. But general relativity shows that gravity can alter the flow of time. Near a massive object, time slows down. Now, imagine a gravitational field so extreme and twisted by rotation that it warps the dimension of time itself into a circle. A closed time-like curve would be a path through this warped spacetime that, while always moving forward from your own perspective, eventually brings you back to an event in your own past. It would be like walking in a straight line on the surface of a sphere and returning to your starting point, but applied to time itself. Your world line would loop back, allowing you to meet your younger self. The most famous theoretical setup for this involves a rotating black hole, specifically a very long, infinitely long and rotating cylinder, which is a different solution to Einstein's equations than a Kerr black hole, but illustrates the same principle of frame dragging taken to an extreme. If this hypothetical cylinder, sometimes called a Tipler cylinder, were to spin at an incredible speed approaching light speed, it would drag space-time around it so violently that it could create these closed time-like curves in the region surrounding it. An astronaut traveling a precise path around this spinning cylinder could, in theory, find themselves returning to a point in space-time before they began their journey. While an actual black hole is not an infinitely long cylinder, the intense frame dragging within the ergosphere of a rotating Kerr black hole produces similar, though arguably more complex, conditions that some physicists speculate could also permit these bizarre timelines. However, this thrilling theoretical possibility is immediately followed by a cascade of logical nightmares that likely render it impossible in the real universe. The most famous of these is the grandfather paradox. Imagine you used such a time machine to travel back in time and prevent your grandparents from meeting. If you succeeded, you would never have been born, which means you could never have traveled back in time to stop them, which means they would have met and you would have been born after all. This is a logical inconsistency, a paradox that violates the fundamental principle of causality, that cause must precede effect. Physics as we know it cannot function in a universe where such paradoxes are possible. The laws of nature seem to abhor this kind of contradiction, and many physicists believe that some yet unknown law of physics, perhaps related to quantum mechanics, actively prevents closed time-like curves from forming. This idea is often called the chronology protection conjecture, proposed by Stephen Hawking, which whimsically suggests that the universe has a built-in security system that prevents time travel to the past, thereby keeping history safe for historians. Beyond paradoxes, there are immense practical and physical barriers. Creating or utilizing a closed time-like curve would require conditions of unimaginable energy. The theoretical rotating cylinder would need to be made of material with infinite density, something that does not exist. Furthermore, the radiation and energy densities involved in such a system might be so intense that they would destroy any object attempting to approach the time travel region long before it could complete the loop. The very act of trying to create a time machine could trigger a feedback loop of energy that would destroy the machine itself. So, while the equations of general relativity allow for the tantalizing possibility of time travel under specific, extreme conditions, the combined weight of logical paradoxes and physical impracticalities suggests that black holes, for all their wonder, will not be providing us with a ticket to the past. They remain, instead, the ultimate symbols of nature's power to warp reality in ways that are more strange and awe-inspiring than any fiction, challenging our understanding without breaking the logical consistency that makes the universe comprehensible. While the paradoxes of time travel might remain confined to theory, the strange mathematics of general relativity opens the door to other cosmic possibilities that are equally fantastic. If a black hole represents a one-way street into a gravitational prison, could its theoretical opposite exist? This idea brings us to the concept of a white hole. In the simplest terms, a white hole is exactly what it sounds like, a black hole running in reverse, where a black hole's event horizon is a boundary from which nothing can escape. A white hole's event horizon is a boundary from which nothing can enter. It would be a cosmic fountain, violently expelling matter and energy into the universe, but completely impervious to any influence from the outside. Nothing could get in. The equations of general relativity are, for the most part, time-symmetric, meaning they work just as well if you run time backwards. If you were to take a film of matter falling into a black hole and reverse it, you would have a perfect visualization of a white hole, matter erupting outward from a central point. However, just because something is mathematically possible does not mean it exists in nature. a white hole would be a tremendous violation of the second law of thermodynamics, which governs the increase of disorder or entropy in the universe. Black holes are fantastic creators of entropy, which is consistent with the universe's overall trend. A white hole, by spewing out ordered energy without any input, would appear to decrease entropy, making it incredibly unlikely from a thermodynamic standpoint. Furthermore, how would a white hole form? A black hole is created by a gravitational collapse, a well-understood process. There is no known physical mechanism that would cause a universe to spontaneously birth a white hole. For these reasons, white holes are considered a mathematical curiosity rather than a serious astrophysical object, a fascinating what-if that highlights the symmetry of Einstein's equations but probably doesn't have a real-world counterpart. A much more popular and enduring theoretical cousin is the wormhole, often called an Einstein-Rosen bridge. If black holes are cosmic dead ends, wormholes are theorized to be cosmic shortcuts. The concept is breathtaking, a tunnel or bridge that connects two distant points in spacetime. Imagine spacetime as a vast, flat sheet of paper. To get from a point on the left side to a point on the right side, you would have to travel all the way across the surface. But if you could fold the paper so the 2 points touch, a wormhole would be a tiny bridge connecting them directly, allowing for instantaneous travel between locations that could be billions of light years apart. This isn't just faster than light travel, it's a way of circumventing the speed of light altogether by bending the geometry of spacetime itself. The mathematics for such a structure also comes directly from solutions to the equations of general relativity. The original Einstein-Rosen bridge described a wormhole that was intrinsically connected to a black hole, but it was later found to be unstable and non-traversable. It would collapse far too quickly for anything, even light, to pass through. To create a stable, traversable wormhole that a spaceship could theoretically navigate, physics requires something truly exotic, matter with negative energy density, often referred to as exotic matter. This isn't just antimatter, which has positive energy. Exotic matter would have the bizarre property of repelling gravity rather than attracting it. This negative pressure would be needed to prop the throat of the wormhole open, preventing it from pinching shut the moment it forms. While certain quantum effects, like the Casimir effect, demonstrate that negative energy densities can exist in tiny amounts in a lab, the quantities needed to stabilize a wormhole large enough for human travel are astronomical and far beyond any technology we can conceive. So, while wormholes capture the imagination and are a staple of science fiction, they remain firmly in the realm of theoretical speculation. No observational evidence for a naturally occurring wormhole has ever been found. Their existence would solve many cosmological problems, like the horizon problem of the early universe, but creating or finding one remains a monumental challenge. They stand as a testament to the incredible flexibility of general relativity, a theory that allows for the fabric of reality to be folded and stitched together in ways that defy our everyday intuition, even if those stitches are too fragile to hold in the world we inhabit. While we have explored black holes that feed steadily from companion stars or lie dormant, some of the most spectacular cosmic fireworks occur when an unsuspecting star makes a fatal miscalculation. Throughout a galaxy, countless stars orbit the central supermassive black hole, most at a safe and respectful distance. But gravitational interactions with other stars can occasionally knock one of these stars onto a highly elliptical, plunging orbit that brings it perilously close to the monster at the center. When a star ventures too near, it meets a devastating fate that provides astronomers with a brilliant beacon to illuminate otherwise hidden black holes. This cataclysmic encounter is known as a tidal disruption event, and it represents one of the most violent processes in the modern universe. The destruction of the star is a direct and brutal consequence of tidal forces, the same phenomenon that causes spaghettification but on a truly stellar scale. The star's own gravity is what holds it together as a coherent sphere of plasma. However, as it approaches the black hole, the difference in gravitational pull across the star's diameter becomes overwhelming. The side of the star closest to the black hole feels a significantly stronger pull than the side farthest away. This tidal force stretches the star, transforming it from a sphere into an elongated ellipsoid. If the star gets close enough, passing within a boundary called the tidal radius, the black hole's gravity wins. The tidal forces exceed the star's own self-gravity, and in a matter of hours, the star is ripped apart. It doesn't explode, it is shredded, pulled apart into a long, thin stream of hot gas like a cosmic piece of taffy. This stellar debris doesn't just vanish. About half of the star's material is flung away from the black hole at high velocity, cast out into the galaxy. The other half, however, remains bound to the black hole. This gas doesn't fall straight in. Conservation of angular momentum ensures it forms a spectacular, swirling accretion disk around the event horizon. As the gas from the shredded star spirals inward at fantastic speeds, it collides with itself, creating immense friction and heating up to temperatures of hundreds of thousands, even millions of degrees. This superheated disk radiates an enormous amount of energy, primarily in the form of X-rays and ultraviolet light, creating a brilliant flare that can outshine the combined light of every star in the host galaxy for several weeks or months. This flare is the tidal disruption event signature, a temporary but incredibly luminous signpost announcing the black hole's presence and its recent meal. For astronomers, these events are invaluable. A supermassive black hole that is not actively feeding, like our own Sagittarius, a star, is incredibly difficult to detect directly. It sits in darkness, its presence only inferred by its gravitational influence on nearby stars. A tidal disruption event, however, turns this invisible predator into a blazing lighthouse. The sudden, bright flare of light at the center of an otherwise quiet galaxy is a clear indicator that a supermassive black hole resides there. By studying the light curve, how the flare brightens and fades over time, scientists can learn a great deal. The rate at which the flare peaks and then decays tells them about the rate of accretion, how quickly the black hole is consuming the stellar debris. The spectrum of the light reveals the chemical composition of the devoured star, providing a form of cosmic autopsy. These events also serve as unique natural laboratories for testing fundamental physics under extreme conditions. They allow us to probe the properties of the black hole itself, such as its mass and spin, by observing how it interacts with and consumes the stellar material. Furthermore, in some rare cases, astronomers have observed powerful jets of material being launched at near light speed from the poles of the black hole during a tidal disruption event. This suggests that the infalling gas can energize and amplify the black hole's magnetic fields, channeling some of the material into these spectacular outflows. Each tidal disruption event we observe is like a flashbulb going off in the cosmic dark, momentarily illuminating the secret life of a supermassive black hole and providing a front-row seat to the final, spectacular death of a star. This brings us to a fact that directly challenges one of the most common and vivid images we have of these cosmic objects. We often hear black holes described as acting like cosmic vacuum cleaners, relentlessly sucking in everything around them. This is a powerful and intuitive idea, but it's also a fundamental misunderstanding of how gravity works. A black hole does not possess some magical, active suction power. Its gravitational pull operates on exactly the same principle as the gravity of any other object in the universe. It just exists in an exceptionally extreme environment. To understand this, let's perform a simple but profound thought experiment. Imagine that our Sun, which has a mass of about 200,000 trillion kilograms, were to instantly vanish and be replaced by a black hole of exactly the same mass. What would happen to Earth? The surprising answer is nothing, at least in terms of our orbit. our planet would continue to trace its same elliptical path around this new dark center year after year. The change in the force of gravity pulling on Earth would be zero. This is because the strength of an object's gravitational field at a distance depends solely on its total mass and how far away you are from its center, not on what that object is made of or how dense it is. Whether the sun's mass is spread out across a 1,000,000-kilometer wide ball of plasma or crushed into a singularity smaller than a marble, its gravitational influence on Earth remains precisely the same. The same principle applies to a black hole wandering through interstellar space. A lone black hole would not actively pull in distant stars any more than a lone star would. Their gravitational fields are governed by the same universal law. So, if gravity isn't a sucking force, what is it? Einstein's theory of general relativity gives us a more accurate picture. Gravity is the warping of space-time by mass and energy. A massive object creates a depression in the fabric of the cosmos, and other objects follow the curves of this depression. A black hole simply creates an exceptionally deep and steep well. The reason it becomes inescapable up close isn't due to some special property, but because its immense mass is concentrated into such a tiny volume. This is the real heart of the matter. It's all about density and proximity. Consider the difference between approaching our sun and approaching a black hole of the same mass. The surface of our sun is about 430,000 miles from its center. You would feel the sun's gravity strongly long before you reach that point, but you could orbit it safely from a distance. Now, imagine compressing that entire mass into a black hole with an event horizon only a few miles across. You could now get incredibly, dangerously close to the entire concentration of that mass. You could, in theory, orbit just a few dozen miles from the center. At that range, the curvature of spacetime becomes so severe that the velocity needed to maintain a stable orbit would have to approach the speed of light. Cross the event horizon and the curvature becomes infinite. All paths lead inward. It's not that the black hole is pulling harder than the sun would from the same distance. It's that the black hole's unique density allows you to get much, much closer to its entire gravitational source, to a point where the geometry of space itself forces a one-way trajectory. The danger of a black hole isn't that its gravity is somehow stronger at a distance, but that its density permits you to venture into a region of spacetime where the normal rules of navigation break down completely. From the mind-bending possibility that black holes could encode all their information on a surface, we now arrive at one of the most profound and radical ideas in all of theoretical physics, a concept that redefines the very nature of reality and was born directly from the black hole information paradox. This is the holographic principle. To grasp its staggering implication, consider a simple, everyday object like a book or a photograph. The photograph is a flat, two-dimensional piece of paper, yet it contains all the information needed to reconstruct a three-dimensional scene in your mind. The holographic principle suggests that our universe might work in a similar, albeit far more exotic, way. It proposes that all the information that describes everything within a volume of space, every star, every planet, every person, every event happening in the three-dimensional world we experience, might actually be encoded on a two-dimensional surface that surrounds that volume. Our rich three-dimensional reality could, in essence, be a projection, a hologram emanating from a cosmic screen. This incredible idea has its roots directly in the puzzle of what happens to information that falls into a black hole. As we discussed, the no-hair theorem states that a black hole can be described by only three numbers: mass, charge, and spin. But this creates the information paradox because quantum mechanics insists that information cannot be destroyed. In the 1990s, physicists like Gerard T. Hooft and Leonard Susskind made a revolutionary leap. They considered the work of Jacob Bekenstein and Stephen Hawking, which showed that a black hole's entropy, a measure of its information content, is proportional to the surface area of its event horizon, not to the volume of the black hole itself. This was a crucial clue. In everyday life, the amount of information something can hold is proportional to its volume. A bigger hard drive can store more data. But for a black hole, the maximum information it can contain is limited by the area of its boundary. This strange fact suggested that perhaps all the information about everything that had ever fallen into the black hole was not lost inside the singularity, but was instead smeared out and stored on the event horizon, like a vast cosmic hard disk with a storage capacity determined by its surface area. To visualize this, imagine the event horizon as being composed of unimaginably tiny pixels, each one Planck length in size, the smallest possible unit of distance in the universe. The information about every atom of an astronaut who fell in, every page of the book they were holding, could be encoded on these pixels in a scrambled holographic form. The three-dimensional astronaut is translated into a two-dimensional pattern on the surface. This doesn't mean the event horizon looks like a movie screen displaying the astronaut's image. The encoding is far more fundamental, dealing with the quantum states that describe those particles. When Hawking radiation is emitted, this process slowly and randomly leaks information back out into the universe, but in such a scrambled form that it would be impossibly difficult to decode. The holographic principle resolves the paradox by stating the information was never truly lost. It was just stored in a different dimension. The principle didn't stop at black holes. Susskind and T. Hooft boldly proposed that if this holographic description works for a black hole, the most extreme gravitational object, then it might be a fundamental property of the universe itself. This is the full, breathtaking scope of the holographic principle, that our entire observable universe with its three spatial dimensions might be a holographic projection from a two-dimensional surface at the cosmic horizon, the farthest distance we can see. Just as a holographic image on your credit card appears three-dimensional but is encoded on a flat, two-dimensional film, our reality of depth, texture, and solidity might be an emergent phenomenon. The true, fundamental laws of physics might be written on a thin, distant shell, and what we experience as reality is a magnificent, dynamic projection from that boundary. The most concrete realization of this idea is the AD-S/CFT correspondence proposed by Juan Maldaisner in 1997. This is a specific, mathematically rigorous duality that provides strong evidence for the holographic principle. It describes a hypothetical universe with a particular type of geometry, known as anti-de Sitter space. Maldaisner showed that a theory of gravity operating in the bulk of this five-dimensional spacetime is completely equivalent to a conformal field theory, a quantum theory without gravity that lives on its four-dimensional boundary. In simpler terms, a complex physics problem involving gravity in a higher dimensional world can be perfectly translated into a different, and often easier to solve, physics problem on a lower dimensional surface without gravity. This correspondence is a dictionary that translates between two seemingly different descriptions of the same reality. While our universe isn't exactly an anti-de Sitter space, the success of this model has convinced many physicists that some form of holography is likely a true feature of nature. What would this mean for our perception of reality? It suggests that the world we see and feel is not the most fundamental level of existence. The solidity of the chair you're sitting on, the vast emptiness of space between stars, the flow of time, all of these could be emergent properties, much like the wetness of water emerges from the interactions of countless individual H2O molecules, even though no single molecule is wet. The universe would be fundamentally pixelated, with a finite amount of information contained in any given region, with the maximum information set by the area of its boundary, not its volume. This idea has profound implications, potentially paving the way for a theory of quantum gravity by showing how gravity itself could be an emergent force, arising from quantum interactions on a lower dimensional surface. The holographic principle, born from the dark mystery of black holes, challenges us to consider that the cosmos may be the grandest illusion of all, a spectacularly detailed hologram whose source code is written on the farthest edges of everything we know. As if the sheer destructive power of a black hole wasn't enough, many of these cosmic engines can also become the most powerful particle accelerators in the universe, capable of launching focused beams of matter with a ferocity that dwarfs anything we could ever build on Earth. These are relativistic jets, and they represent one of the most spectacular and energetic phenomena in the cosmos. While the black hole's gravity pulls everything inward near its equator, its rotational energy and immense magnetic fields can create a powerful exhaust system at its poles, shooting out twin jets of superheated plasma at velocities so close to the speed of light that their effects can be seen across intergalactic space. The secret to forming these jets lies in the complex interplay between the black hole's spin, its accretion disk, and the magnetic fields that permeate the entire system. We've already discussed the accretion disk, that swirling maelstrom of gas and dust that heats to incredible temperatures as it spirals inward. But this disk is not just hot, it's also a turbulent sea of charged particles or plasma. As the disk rotates, it drags magnetic field lines along with it, winding them up like a coiled spring. The faster the black hole and its disk are spinning, the more tightly these magnetic field lines become twisted and amplified. This creates an intense, organized magnetic structure that threads through the disk and shoots out from the regions above and below the black hole's poles. This is where the true launch mechanism comes into play. The twisted magnetic fields act like a slingshot or a gigantic natural railgun. Some of the material from the inner edge of the accretion disk, instead of falling directly into the black hole, gets caught in these powerful magnetic fields. The fields channel this plasma, funneling it along the black hole's rotational axis, which is the path of least resistance. As the particles are accelerated along these magnetic funnels, they gain tremendous energy, being propelled outward in two oppositely directed beams. The process is further powered by the black hole's own rotational energy, which can be extracted through mechanisms like the Blandford-Zenagic process, where the spinning black hole effectively transfers its spin energy to the magnetic fields, which in turn transfers it to the jet. The result is a continuous, highly collimated beam that can maintain its focus over staggering distances. The scale of these jets is almost impossible to comprehend. In active galaxies with supermassive black holes, these jets can extend far beyond the host galaxy itself, stretching for hundreds of thousands or even millions of light years into the intergalactic void. The jet from the galaxy M87, which we famously imaged, is a prime example, extending at least 5,000 light years from its central black hole. What's equally astonishing is how narrow and focused these jets remain over such immense distances. This is due to a combination of magnetic pressure from within the jet and the pressure of the surrounding intergalactic medium, which acts like a nozzle, keeping the beam tightly collimated. When these jets slam into the tenuous gas that exists between galaxies in a cluster, they don't just stop. They create colossal, expanding cavities and shock waves that heat the gas to millions of degrees and generate vast lobes of radio emission, which astronomers can detect with radio telescopes. The impact of these jets on their surroundings is profound and far-reaching. They are a key component of the feedback process that regulates galaxy growth. By pumping enormous amounts of energy and magnetic fields into the surrounding space, the jets heat the gas in the galaxy cluster, preventing it from cooling and falling back into the central galaxy to form new stars. This feedback loop helps explain the observed correlation between black hole mass and galaxy bulge size, as the jet's energy can effectively put a cap on star formation. Furthermore, the particles within the jets are accelerated to energies far beyond what is possible in earthly particle colliders like the Large Hadron Collider, making black holes nature's ultimate laboratories for high-energy physics. By studying these cosmic geysers, we not only witness the raw power of gravity and magnetism, but also gain insight into how the most massive structures in the universe are shaped and governed by the enigmatic engines at their cores. We have witnessed black holes as cosmic engines, powering brilliant quasars and launching relativistic jets across the universe. But what fuels this incredible activity is a property that has its own ultimate boundary. Just as there is a speed limit for matter and light in the cosmos, there is also a cosmic speed limit for rotation itself. Every spinning black hole, from the stellar mass to the supermassive, is governed by a maximum spin limit, a fundamental cap on how fast it can twirl. This isn't a limitation of current conditions. It's a law written into the very fabric of Einstein's theory of relativity for rotating black holes, known as Kerr black holes. This maximum spin is defined by a specific and elegant condition. Physicists describe a black hole's spin with a dimensionless number ranging from 0 to 1. A value of 0 means the black hole is not spinning at all, described by the simpler Schwarzschild solution. A value of 1 represents the maximum possible spin, the ultimate limit. At this critical point, something extraordinary happens to the black hole's inner structure. Remember the event horizon, the point of no return. For a non-spinning black hole, this horizon is a single sphere. But for a spinning black hole, there is a second inner boundary inside the event horizon called the inner horizon, which is notoriously unstable. There is also the ergosphere, that region of dragged spacetime outside. As a black hole spins faster and faster, the event horizon actually shrinks in size. At the maximum spin value of 1, the event horizon and the inner horizon would theoretically coincide and vanish, leaving the singularity inside exposed to the rest of the universe. This hypothetical state is known as a naked singularity, an object that most physicists believe cannot exist in nature because it would violate causality, potentially allowing information to escape from the singularity and leading to unpredictable paradoxes. This leads to a fascinating and almost intuitive cosmic rule. The universe seems to abhor a naked singularity. It's as if nature has a cosmic censorship principle that prevents such an object from forming. The physics itself creates a natural brake on the black hole's acceleration. Imagine a black hole spinning at near its maximum speed, greedily accreting matter from its surrounding disk. The matter in the disk orbits in the same direction as the black hole's spin, a configuration known as prograde accretion. As this matter falls inward, it carries angular momentum, which it transfers to the black hole upon crossing the event horizon, trying to spin it up even faster. However, the closer the black hole gets to the maximum spin, the less effective this process becomes. The reason lies in the geometry of spacetime near a maximally rotating black hole. The inner edge of the accretion disk moves progressively closer to the event horizon. For matter to transfer its angular momentum and push the spin beyond the limit, it would have to orbit at a distance where no stable circular orbit can exist. The physics dictates that any matter that could potentially overspin the black hole simply cannot be captured in a way that allows it to deliver its rotational energy. It is more likely to be flung away or to miss the event horizon entirely. This creates a remarkable feedback mechanism. A black hole acts as its own governor. If it tries to spin too fast, the very act of absorbing matter that orbits in the same direction becomes incredibly inefficient. In fact, theoretical studies suggest that if a black hole were somehow pushed to the maximum limit, any additional matter attempting to spin it up would be repelled. The intense frame dragging and gravitational effects at the threshold would prevent the incoming matter from adding its angular momentum. There's even a counterintuitive way to slow a black hole down by feeding it matter that orbits in the opposite direction, a retrograde accretion disk. This matter carries negative angular momentum relative to the black hole's spin, and when it falls in, it acts like a brake, reducing the black hole's rotational speed. This constant tug of war between prograde and retrograde accretion, along with the natural repulsion at the maximum limit, ensures that black holes are highly unlikely to ever reach a naked singularity state. They are cosmic tops that can whirl at a staggering fraction of the speed of light, but they are forever bound by a fundamental law that keeps their deepest secrets safely hidden behind an event horizon. Looking ahead to the very end of time, we find a cosmos transformed, a universe entering its final chapter in a state known as the heat death. After trillions upon trillions of years, the great cosmic drama of galaxy formation, star birth, and stellar death will have concluded. The universe will have expanded to an unimaginable degree, becoming an incredibly vast, cold, and dilute void. Stars will have long since burned out, their fuel exhausted. Galaxies will have evaporated as their stars drift apart or fall into the supermassive black holes at their centers, which will have consumed the last available matter. In this bleak, far future era, the only significant sources of mass and gravity left will be black holes. They will stand as the final monuments of a once vibrant universe, the last large structures in an increasingly dark and empty expanse. But even these cosmic titans are not eternal. In the profound cold and near-perfect vacuum of the heat death, the process of Hawking radiation becomes the dominant force in their evolution. Remember, black holes are not completely black. They emit a faint glow of particles due to quantum effects at their event horizons. For a black hole of any size today, this radiation is negligible because the temperature of the Hawking radiation is far colder than the cosmic microwave background, the leftover heat from the Big Bang. The black hole effectively absorbs more energy from its surroundings than it emits. However, as the universe continues to expand and cool for eons, the temperature of the background radiation will drop to near absolute zero. Once the universe becomes colder than the black hole itself, the balance shifts. The black hole will finally begin to lose mass, shining faintly into the darkness. The rate of this evaporation is incredibly slow and is inversely related to the black hole's mass. A stellar mass black hole, with the mass of a few suns, would take an almost inconceivable amount of time to evaporate, around 10 to the 67 years. That's a 1 followed by 67 zeros. For a supermassive black hole like Sagittarius, a star with 4 million solar masses, the timescale is even more staggering, on the order of 10 to the 100 years. To grasp these spans, consider that the current age of the universe is only about 13.8 billion years, which is 10 to the 10 years. The journey to a black hole's evaporation spans durations that make the current age of the cosmos seem like a fleeting instant. As a black hole evaporates, a fascinating and terrifying feedback loop begins. As it loses mass, it gets smaller. As it gets smaller, its event horizon shrinks, which increases the curvature of spacetime at its boundary. This increased curvature makes it even easier for virtual particle pairs to be separated, which in turn increases the rate of Hawking radiation. The black hole evaporates faster and faster as it shrinks. In its final moments, this process accelerates dramatically. What began as a slow, imperceptible trickle of particles over trillions of years becomes a runaway cascade. When the black hole's mass becomes very small, its temperature soars, and it begins to radiate away its remaining energy at an incredible rate. The ultimate fate of the black hole is not a quiet fizzle, but a spectacular finale. Theoretical models suggest that when the black hole's mass dwindles to a tiny fraction of its original size, it will undergo a violent explosion. In a final, brilliant flash of high-energy radiation, a burst of gamma rays, particles, and light, the black hole will vanish completely, popping out of existence. It leaves behind not a remnant but empty space and the radiation it emitted over its immense lifetime. This final explosion would be the last significant energetic event in its region of the universe for all eternity. After the last black hole has evaporated, the universe will enter its true final state, a permanent, uniform, and ultra-cold sea of subatomic particles and radiation, spread so thin that no further work can be done and no new structures can ever form. The era of black holes, therefore, brackets cosmic history from their violent births in the aftermath of the Big Bang to their explosive deaths in the ultimate quiet of the heat death, serving as the final custodians of mass and energy before the cosmos settles into eternal stillness. But for all the focus on the stellar mass black holes born from individual stars and the supermassive giants that rule galactic centers, a crucial piece of the cosmic puzzle has been frustratingly elusive. For decades, a vast gap existed in the black hole family tree. On one end, we have objects weighing between 5 and 100 times the mass of our Sun. On the other, we have behemoths of millions to billions of solar masses. What about the middleweights? Where are the black holes with masses of a few thousand or even 100,000 suns? This missing link, known as intermediate mass black holes, has become a primary target for astronomers, as finding them is essential to understanding how the universe builds its largest structures from the smallest seeds. The search for these intermediate mass black holes has centered on two primary cosmic hunting grounds. The first is within the ancient, dense collections of stars known as globular clusters. These spherical swarms, which orbit the halos of galaxies like our Milky Way, contain hundreds of thousands or even millions of stars packed into a relatively small volume of space. Theorists have long suggested that the dense environments in the cores of these clusters could be ideal nurseries for intermediate mass black holes. The idea is that over billions of years, successive collisions and mergers between massive stars, and then the stellar mass black holes they leave behind, could lead to the formation of a single, more massive black hole that sinks to the cluster's center. Finding one, however, requires detecting the subtle gravitational influence of a dark object on the surrounding stars. Astronomers use powerful telescopes to track the motions of stars in a cluster's core. If the stars are whipping around much faster than expected, it points to an unseen massive anchor. Evidence from clusters like Omega Centauri and a cluster in the galaxy M105 has hinted at the presence of such an object, but the case has not yet been definitively proven, making these clusters prime targets for continued observation. The second promising line of evidence comes from mysterious and intensely bright objects known as ultraluminous X-ray sources, or ULKs. These are points in other galaxies that emit a tremendous amount of X-ray radiation, far more than a typical stellar mass black hole should be capable of producing, yet less than the output of a full-blown active galactic nucleus powered by a supermassive black hole. For a long time, the leading explanation was that these were indeed intermediate mass black holes accreting matter at a steady rate. The logic was straightforward. An object's maximum brightness is limited by its mass, a principle called the Eddington limit. If a source is incredibly bright, it must be powered by a correspondingly massive object. However, more recent observations have complicated the picture. We now know that some ULXs are actually neutron stars that are breaking the Eddington limit, pulling in so much material that their radiation becomes focused into beams, making them appear brighter than they theoretically should be. This discovery doesn't rule out intermediate mass black holes as the source of some ULXs, but it means astronomers must now work harder to distinguish between a super-accreting neutron star and a genuinely new class of black hole, using more subtle signatures in the X-ray light. Confirming the existence of a population of intermediate mass black holes would be a monumental breakthrough, as it would solve one of the biggest mysteries in galaxy evolution. How did the supermassive black holes get so big so fast? We see quasars powered by supermassive black holes shining brightly when the universe was less than 1 billion years old. It's a cosmic head-scratcher. How could a black hole grow to billions of solar masses in such a short time, starting from just the remnant of a single star? the growth process for a stellar mass black hole by steadily consuming gas is too slow to account for these ancient giants. Intermediate mass black holes provide the perfect solution. They could have served as the crucial seeds for supermassive black holes. If the early universe was populated by these middleweight black holes, perhaps formed from the collapse of the very first gigantic stars or from direct collapse of dense gas clouds, then the supermassive black holes had a massive head start. They wouldn't need to grow from a mere 10 solar masses. They could start from 1,000 or 10,000, making their journey to supermassive status within the first billion years of the cosmos a much more feasible task. Finding these missing links would therefore complete our picture of black hole evolution, connecting the stellar death throes of individual stars to the rise of the gravitational titans that govern the cosmos. Now, for all the talk of brilliant quasars and violent stellar disruptions, the vast majority of black holes in our galaxy are likely silent and dark, drifting through the void without a companion star to feed upon. So, how do we possibly detect an invisible object that emits no light and is not actively consuming anything? This is where astronomy becomes a discipline of supreme subtlety, relying on the one inescapable signature a black hole always leaves behind: its gravity. To find these isolated phantoms, scientists have developed ingenious methods that watch for the telltale distortions a black hole's immense mass imprints on the fabric of spacetime itself, and the most powerful of these techniques is gravitational microlensing. The principle is a direct application of Einstein's theory of general relativity. We know that a massive object warps the space around it, and this warping acts like a lens, bending the path of light rays that pass nearby. In a microlensing event, an unseen object, like a rogue black hole, passes almost perfectly between Earth and a distant background star. As the black hole moves through its orbit, its gravitational field creates a temporary and moving lens. From our viewpoint, the light from the background star is magnified and focused. The star doesn't twinkle or jump. It undergoes a very specific, symmetric brightening. Its light curve smoothly increases to a peak and then fades away in an identical manner as the black hole moves past our line of sight. The entire event can last from a few hours to several months, depending on the mass of the lens and its relative speed. The beauty of this method is that it doesn't rely on the black hole doing anything at all. It simply has to exist and move through a fortuitous alignment. By continuously monitoring dense star fields, particularly toward the crowded central bulge of our galaxy, projects like the optical gravitational lensing experiment and now the Roman Space Telescope are designed to catch these fleeting cosmic alignments. But a microlensing event alone only tells us that a massive, dark object passed by. To confirm it's a black hole and not just a faint star or a brown dwarf, astronomers need to perform a crucial additional measurement called astrometric microlensing. This involves measuring the tiny shift in the apparent position of the background star. Because the light is bent from multiple paths around the lens, the star's image isn't just magnified. Its apparent position in the sky is minutely distorted. Measuring this incredibly small shift, a task requiring the exquisite precision of the Hubble Space Telescope, allows scientists to calculate the mass of the intervening lens. A significant mass with no detectable light points conclusively to a black hole. In 2022, this very technique provided some of the strongest evidence yet for a solitary black hole, about 7 times the mass of our Sun, drifting through the Milky Way. Beyond microlensing, another powerful method for detecting hidden black holes, even those that may have a few companion stars at a distance, is precision astrometry. This technique involves measuring the positions and motions of stars with unbelievable accuracy over many years. Instead of looking for a temporary lensing event, astrometry searches for the persistent gravitational tug of an unseen companion. Imagine watching a star as it moves through space. If it is orbiting a common center of mass with an invisible partner, its path will not be a straight line. It will exhibit a slight wobble, a rhythmic dance around an empty point in space. This is the same method used to discover exoplanets, but applied to a much more massive, dark companion. The European Space Agency's Gaia mission is revolutionizing this field. Gaia is meticulously mapping the positions, distances, and motions of over 1 billion stars in our galaxy with unprecedented precision. By analyzing the trajectories of these stars, astronomers can identify ones that are being gently tugged by an unseen gravitational source. A star that appears to be moving in a predictable way, but shows a tiny, unexplained deviation in its path, could be signaling the presence of a silent black hole orbiting it from a considerable distance. This method is particularly effective for finding black holes in wide binary systems, where the black hole isn't close enough to strip material from its companion and create an X-ray source, but its gravitational influence is still detectable over time. Each tiny wobble measured by Gaia is a potential clue, a whisper of gravity pointing toward the dark remnants scattered throughout the galactic disk. Together, microlensing and astrometry are allowing us to take a census of the galaxy's hidden population, revealing the silent gravitational architecture that underpins the visible universe. Throughout our journey, we have encountered black holes as cosmic monsters, powerful engines, and profound mysteries. But their ultimate significance may lie not in what they are, but in what they reveal about the fundamental nature of reality itself. Every astonishing fact we have explored, from the singularity to Hawking radiation, points toward a single, inescapable conclusion. Black holes exist at the very boundary of human understanding, and they are actively challenging our most successful scientific theories, forcing a revolution in physics that is still unfolding. The core of this challenge is a cosmic clash of titans happening at the edge of the event horizon. On one side, we have Einstein's magnificent theory of general relativity, which describes the universe on its largest scales. It is a theory of the smooth, geometric fabric of space-time, of gravity as curvature, and it predicts the existence of black holes with stunning accuracy. On the other side, we have the equally brilliant but bizarre framework of quantum mechanics, which governs the frantic, probabilistic world of the impossibly small. It is a theory of particles, waves, and uncertainty. Both theories are spectacularly successful in their own domains. We use general relativity to guide our GPS satellites and understand the orbits of planets, and we use quantum mechanics to build lasers and transistors. The problem is that these two foundational pillars of modern physics are fundamentally, irreconcilably incompatible. They are written in different mathematical languages and describe reality in utterly different ways. Under normal circumstances, we can use these theories separately without any trouble. But a black hole is the one place in the universe where these two worlds are brutally forced to collide. The immense space-time warping gravity described by general relativity operates at a scale so small that the fuzzy, probabilistic rules of quantum mechanics must also apply. This conflict erupts into the open in the black hole information paradox. General relativity, with its elegant no-hair theorem, suggests that information about what falls into a black hole is destroyed forever at the singularity. Quantum mechanics, with its unwavering principle of unitarity, insists that information can never be truly lost. Both cannot be correct. This is not a minor philosophical disagreement. It is a glaring sign that our current maps of reality are incomplete. The paradox is a direct confrontation, and resolving it requires a new set of laws, a unified theory that can seamlessly blend the world of the very large with the world of the very small. This sought-after theory is known as quantum gravity, and it represents the holy grail of modern physics. It would be a single framework that describes all the forces of nature, from the gravity that binds galaxies together to the nuclear forces that hold atoms apart. The center of a black hole, the singularity, is the ultimate laboratory for developing this theory because it is a realm where both infinite gravity and infinitesimal size coexist. Our current laws break down there, yielding nonsensical answers like infinite density. This is not a failure of the mathematics, but a beacon illuminating the frontier where new physics must begin. Promising candidates for this theory, such as string theory and loop quantum gravity, attempt to solve the problem by proposing that there is no true singularity. They suggest that at the tiniest possible scale, the Planck length, the smooth continuum of spacetime, gives way to a discrete, granular structure, like a digital pixel of reality. In these theories, some new quantum effect would prevent matter from collapsing to an infinitely dense point, resolving the singularity and potentially preserving information. The implications of discovering a theory of quantum gravity would extend far beyond understanding black holes. It would revolutionize our entire conception of the cosmos. It could tell us what happened at the very first moment of the Big Bang, another point of infinite density where our current laws fail. It might reveal the true nature of spacetime itself. Is it a fundamental backdrop or an emergent property arising from something deeper? The holographic principle, born from the black hole information paradox, suggests that our three-dimensional reality might be a projection from a two-dimensional surface, an idea that would fundamentally reshape our place in the universe. Black holes, therefore, are not merely exotic destinations for hypothetical astronauts. They are the universe's most demanding teachers. They present us with puzzles that probe the deepest laws of existence, pushing our intellect to its limits. By staring into their darkness, we are not just looking at an object in space. We are looking into a mirror reflecting the very boundaries of our knowledge and the thrilling promise of what lies beyond. So, as we've journeyed from the birth cries of stellar mass black holes to the silent dominion of supermassive giants, one overarching truth has emerged. These are not merely the universe's destructive monsters. They are, in fact, some of its most vital and creative architects. We've seen how their formation in supernova seeds the cosmos with the heavy elements necessary for planets and life. We've discovered how the supermassive black holes at the hearts of galaxies act as cosmic regulators, their powerful outbursts and feedback mechanisms sculpting the growth of their host galaxies, creating the beautiful diversity of forms we see across the universe. They are fundamental to the cosmic order, not an exception to it. The revelation that black holes are not eternal, but slowly evaporate over unimaginable eons through Hawking radiation, forever links them to the quantum world and the ultimate fate of the cosmos itself. And perhaps the most profound shift in perspective comes from understanding that by studying the edge of a black hole, we are peering into the deepest laws of physics. The information paradox and the holographic principle challenge our very concepts of space, time, and information, forcing a scientific revolution that may one day unite gravity with the quantum realm. Each of these facts peels back a layer of the universe, revealing a reality far stranger and more magnificent than we could have imagined. The next time you find yourself under a clear night sky, look toward the constellation Sagittarius, toward the silent, invisible heart of our own galaxy. Know that there, 26,000 light-years away, a 4 million solar mass Titan spins, its presence felt only by the graceful, frantic dance of the stars it holds in its gravitational thrall. The sky is not a static painting. It is a dynamic, living arena where gravity writes the rules and black holes are the master sculptors. We've covered 30 facts designed to change how you see everything, but the conversation doesn't have to end here. Let us know in the comments which fact completely rewired your brain. Was it the sheer terror of spaghettification, the paradoxical glow of Hawking radiation, or the cosmic shortcut of a theoretical wormhole? If you enjoyed this journey to the edge of understanding, make sure to subscribe and hit the notification bell, because there are countless more cosmic mysteries waiting to be explored. Thank you for watching and keep looking